Hi, in this video we will look at each of the key steps that occur in the operation of a time-of-flight mass spectrometer. The diagram shown on screen shows an outline of a basic time-of-flight mass spectrometer with a few parts labelled. Now, to analyse the atoms or molecules present in the mass spectrometer, it goes through a few basic steps. These are ionisation, acceleration, ion drift and detection, and finally data collection, where the information collected by the detector will be processed by the onboard electronics and a mass spectrum will be produced of the sample. Now, the sample under test may be injected at the sample point under low pressure and high temperature to ensure that the sample will be vaporised and form a gas. This is important since the mass spectrometer cannot analyse liquids or solids. If the sample is a solid, it firstly will be heated to vaporise it, or it may be dissolved in a solvent before being vaporised and placed in the mass spectrometer. The spectrometer tube also has all the air molecules removed from it and maintained at a high vacuum. This is also very important since air molecules will collide with the sample ions produced, and this will stop the mass spectrometer from working properly. So let's start off by looking at the first key step, ionisation. In this step, the sample molecules or atoms are converted into ions with a +1 charge. Now, there are two quite different methods commonly used to ionise the sample molecules or atoms. These are electron impact ionisation and electrospray ionisation. Perhaps the most common method used is the electron impact ionisation. So let's start off by looking at how this process works. Here, an electron gun, which is essentially just a filament or wire, is heated up to a very high temperature, somewhere in the region of 2000 to 2500 degrees Celsius. Now, at this high temperature, the hot wire or filament will emit a steady stream of high energy, fast-moving electrons. These electrons will be attracted to a positively charged plate opposite the electron gun. This positively charged plate will attract and accelerate the electrons given off by the electron gun. So if we could imagine these electrons as being fast-moving solid particles, a bit like balls or bullets, then when these atoms or molecules in the injected sample meet these fast-moving electrons, they will have one of their outer shell electrons removed or knocked off. This means that they will have been ionised and a positively charged ion will form. When the sample under test is ionised in this way to form ions with a +1 charge, they are often referred to as the molecular ion. If we call the injected sample X, we can show this using the equation shown. Here, E represents the electron being knocked off the sample X, but you may also see this equation written as shown on screen. And in this equation, the first electron is the electron from the electron gun, while the two electrons on the product side are the one electron from the electron gun and one from the sample atoms which are removed. The second method of ionising sample molecules uses a method called electrospray ionisation. This method of ionising molecules is often preferred for larger molecules which may be blasted to pieces by an electron gun, while electrospray ionisation rarely results in fragmentation of molecules. In electrospray ionisation, the sample molecules are dissolved in a volatile polar solvent, that is, a solvent which evaporates easily, such as water or methanol. Next, it is injected into the sample point under high pressure and through a very, very fine hypodermic needle which has a high voltage applied to it. This results in the sample being ionised and forming fine droplets or a mist containing the ionised sample molecules or atoms. The solvent, being volatile, then quickly evaporates, leaving behind the positively charged sample molecules. This is highlighted in the close-up image of the needle point. In electrospray ionisation, the sample molecules become ionised not by having electrons knocked off or removed from them, as is in the case with electron impact ionisation. Instead, the sample under test gains a hydrogen ion from the solvent. This means that the mass of the sample molecules will increase by 1 unit due to the addition of this hydrogen ion. This is shown in the equation on screen. The next step in time-of-flight mass spectroscopy is the acceleration step. Here, the positively charged ions created during the ionisation step are attracted to and accelerated towards negatively charged acceleration plates. That is, the electrical field created by the acceleration plates will act like a launch pad for the ions and accelerate them to high velocities. Now all the ions, regardless of their mass, are subjected to the same electric field strength. This electric field creates the force needed to accelerate the ions. Now we are going to assume that all the ions produced during the ionisation step have a +1 charge. Now this is important because one of the key features of time-of-flight mass spectroscopy is that all the ions have the same amount of kinetic energy. This is because the force experienced by an ion in an electric field is proportional to its charge and not its mass. So while the kinetic energy of all the ions is the same, how fast the ion actually travels depends on its mass. Lighter ions with less mass experience a greater acceleration, which means that they will have a higher velocity, while heavier ions, due to their larger mass, experience lower acceleration, and consequently, the heavier ions travel at slower velocities. So even though all the ions start together, the ions with different masses separate during this acceleration stage based on their inherent velocities. This sets the stage for the next step in time-of-flight mass spectroscopy, where the ions travel a fixed distance and their flight times are measured. Once the ions pass the acceleration plates, they are essentially out of the region of the strong electric fields. This essentially means that they are no longer being actively accelerated. The ions now enter a long flight tube that's essentially a vacuum chamber. Now in this flight tube, the ions rely slowly on the kinetic energy they gained during the acceleration stage. And since all the ions have the same kinetic energy, the key factor that determines the travel time along the flight tube becomes their mass. Now the lighter ions with their higher velocities will travel the length of the flight tube faster than the heavier ions. Essentially, the lighter ions drift through the flight tube quicker compared to the heavier ions. This difference in the travel times is what allows us to measure the mass-to-charge ratio of the ions later. For example, in the diagram shown, the sample under test contains 3 isotopes of the element magnesium, each of which has been given a +1 charge in the ionisation stage. Now we can see that the lighter Mg24 ion is travelling faster up the flight tube than the heavier Mg25 and Mg26 isotopes, and the order in which the ions reach the detector is determined by their mass. Now it is important to note that the ion drift region relies entirely on the initial kinetic energy provided during the acceleration stage, and the longer the flight tube, the more time the ions have to separate based on their mass, leading to a better resolution in the final mass spectrum. Now the detector plate at the end of the flight tube has a negative charge due to the fact that it contains an excess of electrons which are placed in it from an external electrical supply. So when the positively charged ions arrive at this detector plate, they gain an electron and are reduced. This reduction reaction involves the movement of electrons or a flow of electrical current. Now the more electrons that flow, the more ions there are present. That is, their abundance is high, and this will be recorded by a computer connected to the detector. Remember, the ions will arrive at the detector at various times, since their flight time down the flight tube will depend on how fast they are travelling, and, as previously mentioned, this depends on their mass to charge ratio, or simply their mass if the ions have a +1 charge. By knowing the distance the ions travelled, that is, the length of the flight tube, and measuring their arrival times, the installed software can calculate the velocity of each ion and also its mass to charge ratio. Finally, the software creates a mass spectrum. This spectrum is simply a plot of the mass to charge value on the x-axis versus the intensity, that is, the proportion or abundance of ions on the y-axis. The mass spectrum provides a visual representation of the different ions present in the sample and their relative abundances. Hi, thanks for watching. If you found this video helpful or would simply like more information, then why not visit the website that accompanies these videos? The links are in the description below. If you enjoyed the video, then please consider liking and subscribing. Thank you.